Hello everybody and welcome back to, I guess this would technically be the first video for Fundamentals. My very first video on this channel is actually for the final for Fundamentals of Pharmaceutics to cover some of that content. But I wanted to swing back, and then this is also the second exam, so that's a little confusing. The reason I don't do Dr. Garrett's exam, or at least haven't done one yet, is because I don't think I could teach it all that well. It's kind of just knowing structures and understanding the Henderson-Hasselbalch equation, which you'll get a little more of on this exam, which I will go through. But I just figured I want to make this for essentially kind of more of the math related problems. I can teach that a little more accurately just because it's, there's always one right answer. And I can kind of show how to go about solving these problems. This is essentially a review of the 2023 exam. Dr. Casting and Dr. Lee are very nice, and the fact they give us old exams to work through, and each year they're pretty similar. So if you can get these old exam down, you'll generally do pretty well. But with that, let's hop into this. So for kind of this first problem, we're given two compounds. We're given ketoprofen and indomethacin, and we have to do essentially some math with them. So what are we trying to solve in this first one? So we're looking at the ketoprofen, and we want to know what its ideal solubility is at 25 degrees, which is pretty standard. There's two solubility equations you will need to know. For this first one, this is ideal solubility. This one's a little bit easier. And the key about ideal solubility is it does not involve this log K oct. The solubility in water will. That's kind of where that comes into play. And the reason for this is essentially if, it's an emulsion of oil and water, not everything's going to dissolve evenly. So that's kind of why this is an ideal solution where we're assuming everything dissolves evenly and we don't need to worry. So what is that equation? It's pretty simple. It's the log of your solubility, so that's usually denoted as like x squared, times negative 0.01, your melting point, and this is in Celsius. So that's really nice that all our melting points over here are also given in Celsius. We don't need to worry about that. Minus 25. And yeah, that's just the equation. So we can solve this really quickly. So we have negative 0.01 times, for the ketoprofen in this case, it's 93 minus 25. We put that in our calculator. We get negative 0.01, 3 minus 25. We get negative 0.68. And now, since this the solubility value over here is in a log, right? We essentially need to raise both sides to the 10 to kind of negate this log. So when we do that, we get that x squared is equal to 10 to the negative 0.68. And that is equivalent to, you get 0.208. And that is the most similar to this one. That's D. So that's how you solve an ideal solubility problem. This next one is going to have us solve kind of, I don't want to call it unideal solubility, but it's water solubility. And it's essentially where we have that log K oct. So I'm going to erase some of this work just because I really did not give myself a lot of space to do this problem. But you can always go back and see how I did that for the first step. So now we have to do water solubility, right? Or in this case, it's in the stomach. So how do we know that's water solubility? You kind of just logic through it, right? Think about it. The stomach is kind of a giant vat of solution in a way. It's all liquid for the most part. So it's like, okay, it's liquid solubility. So for this, we have a slightly different equation. It's a similar concept, but it's 0.5 minus that 0.01 melting point minus 25, and then plus our log K oct. So, and this is important too. This might be changed sometimes. This table is nice enough to give us the log K oct. Let me make sure I write log here because that is important. Sometimes this table will just give you K oct. And if that's the case, you need to take a log of this value. So let me erase this just because this is really important. And I don't think they've tried to trick us with it in recent years on the exams, but this used to be this way on the old exams. This is log K oct. So just make sure your table is log K oct and not just K oct. Otherwise, you need to take a log of it, which obviously isn't hard to do. You can just plug it in your calculator. but just you don't want to forget it, right? Because it could mess up your entire problem. And we're just trying to see essentially which one of these values is higher. You may remember that just learning this in maybe biochem, right? K-oct is kind of like lipid solubility, which usually means more absorption to the body. Um, but in this equation, very generally, what Dr. Casting is trying to show us is that temperature actually plays a bigger role. And because these values right here are very similar, right? They're essentially equivalent, but indomethacin is slightly higher. So we're expecting indomethacin to be higher just based on the K-octs. But let's go through this really quick. So essentially set up two equations. I'll do the ketoprofen first because it's on top. 93 minus 25 plus 3. 5 Sorry, I'm just typing this into my calculator rather poorly, I might add. 0.01, 93 minus 25 plus 3. So for this one, we get 2.82. And remember, since on this other side of the equation, I didn't write it down, but it's the log of the water solubility. So we do need to raise this to the 10th. So 10 to the 2.82. We get value of 660, roughly. We'll do it for indomethacin now. 5 minus 0.01. 9 minus 5 plus 3.08. Right here we get a value of 2.16. Raise that to the 10th. And we get 144. So you can see here that it's really these things in melting point. And this is another thing to mention, is that things with a lower melting point are generally much more soluble. So in this case, it's actually the ketoprofen that is more soluble, even though that log K-oct was lower. And you can see how that just difference in 50 degrees of melting point can be so influential in kind of changing those values. So for this next one, I'm just erasing that. It wants to know the approximate solubility of ketoprofen in a biological membrane. How do we do this? So this comes down to just by definition what the log of K-oct is, or what K-oct is itself. And essentially it is solely the ratio of something, how much something would dissolve in oil versus how much it would dissolve in something aqueous like water. So you may remember that kind of a really low value, like something below 1, will generally be more water soluble, but a value that is above 1 will be more oil soluble. So how do we get this? It's actually really simple. All we have to do in order to get this, we have a log K-oct. In order to find the K-oct, because that's essentially all this is asking, we just have to raise this to 10. So what's 10 to the 3 in this case, right? Because we have a value of 3 for ketoprofen. That's just 1,000. And what this 1,000 means is it's just 1,000 to 1, oil to water. So with that, we get B. Not too bad. Next up, we have this problem. One of these two compounds has also become a successful anti-inflammatory based on the properties. Which of these is most likely better at this? So this comes down again to, it's essentially the same kind of question as question 2. It's trying to throw you for a loop. And all it's trying to show is that log K-oct is not that important in solubility. So there's some other factors that also go into solubility, right? There's size of something being able to cross the membrane. Smaller molecules can cross the membrane more easily. So in this case, you can see that's also ketoprofen. But it's just this difference in this 144 for indomethacin, right, that we calculated versus the 660. This 660 is so much more important than any other value. The answer is ketoprofen. And it's just that that water solubility that essentially is going to determine how soluble your product is. This next problem is pretty easy. It's negative log of the concentration of hydrogen ions, and this is just the definition of pH. It's 1.3 times 10 to the negative 6. Plug that into your calculator. We get 5.89. I think a lot of us has been doing this since high school chemistry, right? And I think most people get this problem right, so don't get it wrong. Now you know how to do it, in case you didn't before. Okay, so now let's do some Henderson-Hasselbalch. This doesn't have to be too hard. You are given this equation, or at least you were when I was still taking this. I know Dr. Casting said he might not include this on the equation sheet, but I can't imagine he takes it off, unless he tells you guys otherwise, obviously. But for this first equation, just knowing that Henderson-Hasselbalch is equivalent to pKa equals pH plus the ratio of the log acid over the base. I accidentally, when I was copying this over, I forgot to give the pKa on here. It's 3.86 for this problem. So it's just 3.86 minus our log, which is 7.4. And this is me rearranging the equation slightly because we're going to have to do this anyways. Log A over B. We do 3.86 minus 7.4. We get negative 3.54. In order to get rid of this log on the side, we have to raise everything to the 10. So 10 to the negative 3.64. We get a value of 0.0028 equals the ratio of log A over B, which is fine, right? Because we're doing things in terms of log A over B anyways, it doesn't really matter. If it asked what the ratio of base to acid was, we'd take the reciprocal, but it's not. So we can just simply answer A. Not too bad. And this is actually 3 zeros. I just forgot to include a decimal point when I was saying that, but the answer is A. Okay, so for this next one, we have lactic acid has this pKa. Oh, I had it down here. That's funny. And 0.25 moles of sodium is prepared. How do we kind of find the buffer solution of the solution, or the buffer capacity? Oh, just kidding. I lied. I'm not reading the problem. I was reading ahead. It's actually just asking us for pH. So this one isn't too bad. It's just another Henderson-Hasselbalch. We set it up, and we got our pKa equals pH plus log A over B. And so we're solving for pH. We can rearrange this to be pH equals pKa minus log A over B. We have our pKa, right? That's 3.86. And we have this many moles of lactic acid and its sodium salt. So the buffer has 0.15 moles of lactic acid. That's a really good hint that it's an acid. And whenever something is a salt, especially with sodium, you can usually assume it's a base. So what we do is we do minus log our acid concentration, which in this case is 0.15 moles, divided by 0.25, right, of that base. And that'll get us our pH. So let me really quickly type this into my calculator. 3.86 minus the log of 0.15 divided by 0.25. We do that, we get 4.08. Hey, and look at that, it's D. It's the right answer. Perfect. Okay. So next up, we're looking at ionic strength. This is the problem I was looking at a second ago without reading. And essentially, it just wants to know ionic strength of this last problem. So what are the ions in this solution? Remember, the key to ionic strength is that it is essentially just ions, right? So for example, this lactic acid, I don't know exactly what lactic acid looks like. I'm just going to pretend, draw this. We can tell me how close I am in the comments, right? Boom. I think this is what lactic acid looks like. It will never be deprotonated here, right? Or at least never to a significant extent. This is not an ion. I don't see a plus or a minus charge on this molecule anywhere. So if we know that this is like a non-charged form of the molecule, we can just forget it entirely. So this 0.15, just cross it out, right? Now, would there be some of this that would donate a proton to some water and make hydronium ions? Yeah, there would be. But the thing is that pKa is so high right? That 3.86, it's not really going to contribute that much, so I'm just going to ignore it. But what we do have is we have the 0.5 moles of the sodium salt. Don't know why I erased that one, I'm going to have to redo this. We have this Na plus, this O minus, and then however I drew this before, you can see all of a sudden, oh, we do have plus and minus charge, right, in this salt. So what we have to do is we have to find the concentration of each. Well, if there's 0.25 moles of this salt, and these are split up, we have 0.25 moles of this and 0.25 moles of this. And we just add those. So we get a total strength of 0.5 molar. But the key is we have to multiply this by 1/2, right? Because if you remember, I believe this equation is the sum of the charge squared times the molarity times 1/2. And we got lucky here, right? The charge on both of these is 1, right? So that's 1 squared. So that just cancels out. Had this been instead, for example, an ion that looked, it was like, let's say the salt was connected to a calcium, right? And then, I don't know, like an O with a minus charge, like just calcium oxide. Let's think of that. This is +2, -2. If this was 0.15 molar of each, it wouldn't be an ionic solution. Let me finish up the problem before I do this. So we have 0.5 molar is the sum, right? But we multiply this by 1/2 because that's the formula I was just describing. We get 0.25. So for that, it is E. Right, but let's go back to this equation because this is something I want to touch on just because I don't want to lead you astray for your exam. I want to make sure you guys understand this. So this equation, right, takes into account this charge, sum of charge squared times molarity. Calcium ion has +2, oxygen ion has -2, and this salt, let's say it has a molarity of 0.25, we'll use the same one. These charges, right, 2 squared equals 4. So even though there's the same concentration that we had in this problem, this 0.25, this is actually going to be 4 times higher than problem 1. The final answer to this would be actually just a charge of 1 in the solution, because it would be 4 times 0.25, or instead of 4, you could write it as 2 squared times 0.25, plus another 4 times 0.25 for that oxygen molecule. You'd have 2, and then you multiply that 2 by 1/2. That's 1. So that's kind of how these charges can change up these problems. But in this problem, it was really easy. Since it's just a +1 and a -1 charge, we didn't even need to worry about that step. But just so you know, because I think that has been on previous exams, he obviously didn't do it for 2023, but just kind of so you're aware. This last problem isn't too bad. It's just the buffer capacity equation. Words are difficult. And this is a pretty simple equation. It is literally just 0.576 times your concentration. So 0.576 times concentration of 0.15 molar. And we get 0.0, sorry, there's a 0 in front of that, 864. That's closest to this. So again, really simple equation there. It should be on your equation sheet as well. So yeah, that's buffer capacity. Okay, so now let's go over this graph problem. We have 2 compounds. We don't know what they are specifically, but we can kind of extrapolate it, right? One of these is going to be morphine, and one of these is going to be phenobarbital. This graph essentially shows their aqueous solubilities. The key to this problem is not to get super confused because it says the injectable forms have salts. And quite frankly, I think the easiest one to solve for is the phenobarbital being mixed with this sodium plus, right? So in this case, in this phenobarbital sodium salt, this is the conjugate base of phenobarbital, right? It's bound to something positive. So if we were looking at the salt, this would be the base. However, what this problem is asking, and I actually got this wrong on our exam, I remember when we took it, is it just wants the pure compound. So if this is a conjugate base, that means regular phenobarbital is an acid. And if you recall from class, Acids are more soluble at higher pHs, right? Because they're more likely to be like negatively charged, and things with charges are more soluble in water. Bases are the other way. Bases are more soluble at lower pHs because they're more likely to be positively charged. So like base plus or H base plus. So from this, right, we just distinguish that phenobarbital is the acid. It's acting what compound X is, aka what the base is, and in this case, the base is morphine. And we kind of just did that through process of elimination. You can do a similar kind of logic I just did with the salt form there. Um, this is actually a salt of sulfuric acid, which I personally just find to be a little bit confusing to visualize. If that works for you, that's great. But I like these really simple one ion kind of systems. And that's how I'd recommend picking out an acid or a base on a problem like this. So this next one is just asking us what the pKa of the protonated form of compound X is. How do we do that? This is a little abstract, I will admit, but it's essentially is double this value, this very last edge value, right? And then we can trace that over here in the graph. And again, it's a little abstract. This will be the exact same for the acids. It'll be double the value. It'll be over here instead for an acid, but for the base, we have a value here, right? And I'm not super good at eyeballing logs, at least not anymore. I definitely was in this class. I can see here that this value, it's about, maybe 20% of the way up. And this isn't a log scale, so I do need to think. But I would say double would be about right here. Remember, it's exponential, so it falls off a little bit. You come over here, you trace this. I'm thinking this personally looks to be, it's a little over this line here, right? Luckily, this problem was nice. 7.9 ceiling, that makes sense, right? Because if I did 9.1, that'd be like all the way over here. Well, that's not double. That's like right where it is. And 6.8, I mean, that'd be way closer to here. That's not right. So this problem gives you some leeway, but just knowing double kind of that endpoint is where you have your kind of pKa. So it's like, I guess the way if I had to write this is pKa equals 2 times your like min solubility. And so if that equation helps you visualize it a little bit better, that's kind of how you do it. But just solving it graphically is pretty much all you'll ever be asked to do. So I wouldn't lose too much sleep over it, as long as you can do what I just did. This next one, we essentially just want to know where we can make 10 milligrams of that phenobarbital, which remember is our acid. So we simply come over to our 10 milligram mark. It's right here. Trace down. What's closest? It's not 7, it's not 10. 8.3 makes the most sense. That checks out. This next problem is a little bit harder, just because this doesn't work super well graphically. It wants to know what the pH ranges are for 10 milligrams of morphine in the solution, 1 milligram of phenobarbital. So I'm actually going to go back and I'm going to change this to be blue, just because I think that'll be easier to represent visually. So, okay, 10 milligrams of morphine. Where do we have 10 milligrams of morphine? We have that right about here. So we're going to make this our dot right here, draw it in blue. And what I always like to visualize, right, is the range it's soluble is going to be everything where this line is like higher. So this goes this direction for a base, right? Because over here, right, we can get up to 100 milligrams right here, or even like closer to 1,000 up there. So this line will go this way for our blue. So essentially anything less than a pH of 6 is reasonable. Our phenobarbital in red, our acid, where's it 1 milligram? It's actually right here at this intercept. Acids are the same way, right? They get more soluble if they go this way. So we essentially have to find the values between these two ranges, and we get that for this, since it's higher this way and lower this way, these solutions are possible between a pH of 2 and 6, which is our answer D for this problem. Okay, so now let's go over some kind of like true-false questions. A lot of these are reused every year, so I don't want to tell you to memorize them, but you can kind of just memorize them. For this first one, carbonic acid does not have a pKa close to 4. It's not a useful buffer in the blood. This is false. There's other factors that go into this, right? Because bicarbonate, for example, carbonic acid is this molecule. Bicarbonate does have a pH close. So, and then there's obviously also CO3 minus, like -2, I should say. There's a lot of different forms that can be useful in the blood to kind of make that buffer system work the way it needs to be. So for this next one, blood buffer relates to this. Is this exclusively in the fluid of the blood? This is false because there's obviously carbon dioxide. This kind of bubbled into the blood. And this can be converted, I forget what enzyme it is, into H2CO3, right, to be part of that blood buffer. So for this next problem, it's talking about polyacrylates. This is a type of sort of for gels. And it's just asking which is true. So this is kind of, you just need to know it. I'll draw one really quick, or roughly what one looks like. So it's kind of like this, basically just repeats of these in like a carbon chain. And these are all minuses. So carboxylic acids, is there repeating chains of those? Yep, pretty much. So we know one is correct. They must be neutralized with the base. So the whole reason these work and why I had to draw these O minuses right here is they do need to be base stabilized. It's kind of the repulsion of these O minus charges that stabilizes it, makes it a stable form. So number 2 is true. And then are these not salt tolerant? This is also true. Things like Na plus, for example, if you were to dump a bunch of those positive charges would kind of mess up those O minus repulsion charges. It would make it not stable. So for this one, it's all 3 of those, and that's just kind of a picture of how they work physically. Yeah, just very surface level. This question is used, I think, for the last couple of years. It will probably show up again in your year, so just something to be aware of. For number 17, which of these compounds would have an appreciable buffer capacity? What makes a good buffer? It's essentially things that will accept and donate protons, right? So in this case, there's only like really uh, 2 good answers here, and it's these ones right here. Sulfate on its own really does not like to accept protons. It will very rarely, but it's not a good buffer. And obviously K2, right? It's an alkali metal. It doesn't really want to. It will pair up with OH in the solution, but it won't really make a buffer. Versus, for example, KHSO4, right? This HSO4 molecule right here, -1 charge, can accept or donate a proton. That makes it a good buffer. So number 2 is a good buffer. H2SO4. Almost immediately when this dropped into water, one of the protons will dissociate just because it's such a strong acid. So then we have HSO4, again, back to this molecule. So essentially our answer for this is D. It's 2 and 3, just because it's basically things that will willingly accept or donate a proton. This next question is very similar in a lot of ways. It's using slightly different terminology. It's saying, what is an amphilite? Wow, how do you miss circling something? Jeez. That was impressive. Anyways, what is an amphilite? Essentially, it's things that can have a plus or minus charge onto them. So water, for example, is our first example. We know we can have H3O plus and we can have OH minus. Wow, perfect. Amphilite. Good. 1 down. HCO3, we can have H2CO3. That's gained a proton. We can have CO3 minus 2. Wow, lost a proton. The last one that's kind of up for debate is that glycine molecule. This is actually really nice in the sense that if you draw it out and how it would normally look in water, if you remember kind of the structure of an amino acid, the basic structure is going to be N. In this case, it's H3. This makes this a plus. We have that carbon that can vary. We have O minus, and this is like in a pH of 7 usually. And this is true for most amino acids. So you can see here, we actually have a plus and a minus. That just automatically makes this an amphilite, right? Being able to get more positive or more negative charge. So it's E. Not too bad. So it's really just the key to that one is knowing how glycine kind of, what it is, how it would look normally. For this next one, poor solubility. in an oil-based formulation. So this is key here. And we kind of talked about this before uh, in the first couple of problems when we were doing that math. If you remember, log K oct is a factor, but temperature is the biggest factor. And remember that a higher temperature is a lower solubility, as we saw in that problem with the ketoprofen. So we already know that high melting point is at least one of the answer. Lack of ionizable functional groups. Uh, so for example, that'd be probably like an alkane chain, right? Well, we know that alkanes and non-charged molecules are actually kind of fine in oil-based solution, right? It's not like water where you want those ionizable functional groups, right? Because like water, for example, um, you can have those hydrogen bonds. That wasn't a hydrogen bond. Let me think of something. Hey, look, ammonia. That can make a hydrogen bond. Wow, there we go. Right, in these charged species. But like this alkane isn't going to do really anything. So it's not this. And then high oil water partition coefficient. Remember that this is an oil to water ratio. A high coefficient would actually mean it goes up in oil. It's more soluble. So it's not 3. So the answer is actually only A right here, right? It is only the melting point that would lead to poor solubility in an oil-based solution. For this next one, I'm talking about polyacrylate gels again. That's what I kind of drew over here, right? Those things with the negative charges and the carboxylic acid groups, widely used as ingredients. Again, I think this is just the exact same question repeated. Oh, that's so funny. I didn't even notice that. Well, anyways, I guess we had a duplicate question in our exam last year. That actually seems familiar. Answer is still the same. So yeah, there we go. Boom. And then for 21, ionic strength is a major factor in influencing which of the following stabilization mechanisms. Um, this is something you kind of just have to memorize, but you can kind of get it from the name. Ionic strength, right? When I think of ionic, I think of things like sodium chloride, right? Like those plus and minus charges coming together. If you see something like electrostatic, then that stands to reason. Van der Waals, you wouldn't get that. Van der Waals interactions would be like alkanes, and you might have like those weird kind of temporary hydrogeny bonds, changes in charge between them. So it wouldn't be that. And then steric stabilization, well, these are really small ions, right? This sodium, this chloride. These aren't going to have steric hindrance to stabilize them. So the answer is actually A only for this one. Okay, so here are some more questions that tend to pop up every year. For this next one, you're adding a polymeric emulsifier to the solution. Now, when I see a word like polymeric, I usually think polymer, right? So think a large, like carbon chain kind of deal, anything really big. And what do we think when we think big? We usually think of sterics, if you remember from like OChem. Just kind of that steric hindrance, right? In this case, it's not just hindrance, but like it's so complicated, it kind of stabilizes the molecule. Think of something like Velcro, right? A bunch of strings and hooks that kind of work together to form a network. And that's really all this does, right? Electrostatic is only with ions, and then van der Waals, I don't even know what that is. I think that's fake, to be honest, or maybe it's something. I don't think we ever talk about it in this class, though, so the answer is only B for this one. This is, again, a question that gets reused like every year. This next one, it's which of these were important for the mRNA vaccine. It's just all of these. You kind of talked about this on the first day. The nucleosides, the lipid delivery. Then this literally just says, and even more basically. Yeah, there's a lot that went into that vaccine. So that's why this one is E. Just remember that it doesn't get, or at least until now, I don't want to say it never gets changed, but the wording has not changed in previous years, and this one kind of always gets asked. So just, be aware of that. Um, for this next one, why is caffeine kind of used in the solution for lipophilic solutions? Um, Basically, this is one I didn't know when I went to the exam, or maybe I did. Maybe it was a question the previous year, but you can kind of reason it out, right? Caffeine binding covalently. When I think of a covalent bond, I think of like a carbon to carbon bond. That's not going to happen without like an enzyme, so you can pretty much cross off one right away. Caffeine associates in aqueous solutions due to favorable pi electrons. I don't know that, but I see the word aqueous, right? And caffeine's pretty well water soluble, so I'm good with this one. And then planar aromatic compounds form stacks. Again, I don't really know that, but I know caffeine has some rings. I think it's like that's a six-membered, I promise. Six-membered ring and like a five-membered ring maybe, or maybe it's two six. membered rings. I really don't remember, but again, this is just kind of one you memorize and you just pick D. It just, kind of logicking through, right? Just recognizing words like covalent, realizing, hey, this sounds really wrong, is all that question's asking you to do. Um, this next one's another really similar concept. It's what is the most likely reason for this? Important for patent protection. This one's not true. Since the dihydrotamine, you can't patent specific salt forms of something, so this isn't true. Important for pharmacologic, again, probably not. It's a counter ion. Least expensive salt. I mean, logically, like I'm sure a chloride would be cheaper than a mesylate. It's not this one. Naturally occurring, I doubt it because I don't even know what mesylate is. So the only answer that makes sense for this one is E. Again, just kind of common sense logic can get you there. This next one takes a little more actual kind of skill. It's more of a logic question than anything. It's talking about a solution containing salt and then also isoleucine. And essentially it says it's at the isoelectric point. Now what that means is I don't know what isoleucine looks like, but really quick, if I'm just to draw something that kind of looks like an amino acid, right? It's it's essentially saying at the isoelectric point that, oh God, I forgot what an amino acid looks like. We'll just say this. It basically means that we have one charge on here that's negative, and then another charge on here, this will be a 3, that is positive, right? And these kind of charges balance each other. It becomes a Zwitterian or a Zwitterion, whatever you want to call it. And when you have a Zwitterion or a Zwitterion, it never contributes any ionic strength. So basically, when we're doing our ionic strength calculation, we actually just ignore isoleucine if it's at the isoelectric point. So all we really have to do is we do 0.15 molar of the sodium plus 0.15 molar of the chloride, and then we from here it's pretty simple. We just divide by the 2 or multiply by the 1/2. We did a more complicated version of this in the previous problem made, so it's just 0.15. And with a lot of those simple salts, it's always just going to be their molarity if it's a +1, -1 charge. This next one's a bit more complicated. There's 2 buffer equations you kind of need to know. They will be on your exam sheet, so don't worry too much about that. But essentially, you need to be able to recognize for this problem that HCl is a strong acid. Just kind of like sodium hydroxide is a strong base would be another way to like make this problem. So if you have 0.2 normal of it, right, the concentration times 2.3, this is just a constant, will get you your equivalence and your buffer capacity, and in this case, that's 0.46. So it's E. And then finally for this last problem, this uses the other buffer equation. Since this is a weak acid, weak base combo, what we need to do is add their concentrations. So we have our boric acid is 0.1 molar plus our sodium borate is another 0.1 molar. And then we multiply this, instead of by that 2.3, we multiply it by 0.576, I think it is, or maybe it's 6.7. I might have it backwards. I'm not looking at the equation sheet. But when you do that, it's 0.2 times 0.576. You get the answer that's closest to this one. I got 0.1152. This rounds up, it's A, and that's kind of how you solve this one. So again, 2 different buffer equations, this one using 2.3 for strong acids and bases, this one using 0.576 for weak acids and bases, but that's kind of when you use those. Okay, so for this next one, the concept it's basically wanting you to know is polyacrylate gels. We've talked about a little bit. They have like these carbonyl groups, right? These minus charge, and we kind of already discussed how they're destabilized by positive charges. So really all this problem is asking you to do is which one of these ions contributes the biggest positive charge with its ions. And essentially we have like NaCl and KCl, right? These are both +1s, and NaNO3 actually. These are all +1, so they're probably not the biggest, so we can just cross those off. Because you see here we have Na2SO4. This one's good. This has 2 equivalents of positive charge. But then we have this aluminum chloride here, and if you don't know, on the periodic table, aluminum has a charge of +3. You can also kind of tell that because there's 3 chlorines. So it's going to be this one. It's going to be E, just because that contributes the biggest positive charge. It would destabilize this gel. the most quickly. This next one, this is kind of just a question, or can you recognize counter ions? And ones you can just immediately cross off is things like sodium chloride, disodium phosphate. They won't form counter ions because they're just salts in solution, so we can just immediately cross those off. So it really brings that down to a 1 and 3, which is nice. And it's asking us what can't we mix with heparin sodium. So what do we know about sodium? It has a plus charge, meaning that heparin probably has a minus charge. So right away what we can assume, right, is that anything that has kind of a positive charge, any of the other ions would be fine with heparin. So for example, potassium, as in right here, has a positive charge, meaning penicillin has a negative charge, meaning we're fine to mix heparin and potassium. Phenobarbital has a sodium, right? So sodium is plus, phenobarbital is minus. This is fine to mix with heparin. On the other hand, sulfate has a -2 charge, meaning gentamicin has a positive charge. Now the reason this is bad, right, is essentially the positive charge from gentamicin will kind of fuse with the negative charge of heparin. These might form kind of like an ionic bond, and since these are organic molecules, they might clump up. They might have reactions we don't want, which is why we aren't able to administer gentamicin and heparin together. And that's kind of what you're always looking for. Does the drug bind to another drug as opposed to another salt? And if you can answer that, then you've already pretty much answered the question. This next one is kind of reading a graph. We have propylparaben, which we're just trying to dissolve in a solution. The propylparaben itself actually doesn't matter. What we're looking for is the glycerin. So over here on the chart, we can see the glycerin is read as these triangles. So we're looking at this curve right here, and it's actually really nice because we already have some lines on there, so that it helps us out a little bit. But just in case those weren't there, that's how you'd figure that out. And we want a 20% volume for volume solution of glycerin and water. And pretty much how we do that is over here is our volume of cosolvent. You can see these tick marks down here on this graph. We have 1, 2, 3, 4, 5. So we can assume that's 5 again, meaning that each time this goes up by 0.1. So if we have 20%, 20% is equal to 0.2. That's our second tick mark, so right here. And we just basically have to draw up, and then boom, this is our solubility. So where are we here? If we draw over, you can see we're about right here. When we look at our answers, what do we have? So since this is 10 to the -3rd down here, this is going to be 2 zeros after a decimal point, and then one other number. And what numbers on here look like that? Well, I'd say the closest one is we're above this 1 tick mark, right? Because this is a log scale. We're closer to that 2 or 3 tick mark. We don't have 0.02. So instead what we'll do is we'll do, or I'm sorry, 0.002. We're closer to 0.003. So this will be A for this one. And that's basically just reading a graph. That one's not too bad. This next one's a little bit more complicated. And I think the key to understanding this one is just remembering kind of how concentration in a solution works. So we have 0.02 of propylparaben and glycerin stirred into an equal amount of water. So this actually helps us out here, right? Equal amount of water and equal amount of glycerin means we're right here at this 0.5 tick mark. So that's really good. But it's not as simple as drawing up to this 0.02. What we actually have to do instead is draw up to 0.01. And why do we do that? The reason we do this specifically is because if you think about it, we have this amount dissolved into glycerin, right? And we'll just call that X. But if we have another amount stirred into water, we'll just call that volume of water W. I'm not doing the best job explaining this. Well, I can keep going this way, actually. So if we have a concentration of 0.02 over X, right? This is our 0.2 molar propylparaben and glycerin. When we add that water, we'll have to add W. So then if we have this, right, and we know that X is equal to W, so we establish down here, because this is an equal concentration of glycerin and water, 0.02 over 2X, if we just substitute in X for W, and then we actually have a concentration of 0.01 molar. So that kind of changes where we're at. Where is 0.01 molar on a graph? Well, if we draw up, 0.01 is equal to 10 to the -2. So we're drawing up here. And since we're over this glycerin line, we're insoluble. And actually, if you'd forgotten that step on this problem to divide, it wouldn't really matter, right? Either way, because we'd be up here instead. That's still insoluble. But just remember that for the exam, just to do that extra step, because I think on 2022's exam, it was like that, where you had to have that dividing step in order to get this problem right. So again, it's just important, but for this problem, it didn't matter. So we were just able to establish that it was unstable because it fell right there, roughly. And then for this last problem, this kind of problem is very abstract. It involves a lot of complex thinking. We know that this compound is soluble in water at this frequency and soluble at 100 milligrams per milliliter in ethanol. I like to solve these graphically. I know there's a way to solve this with an equation, but I'll kind of show how you can solve it graphically. So what you can do is you can draw your own graph, and we want to do a log scale here on our own. How do we do that? We know that in water, right, when there's 0% cosolvent, so this will be our cosolvent axis, similar to how we have that down here. We have a concentration of 0.1, right? Because when this is only water, it is 0.1 milligrams per liter. If we go up a log, we have 1 milligram. If we go up again, we have 10 milligrams. And if we go up one final time, we have 100 milligrams, right? And this is where it'd be soluble in ethanol at that 100 milligrams per milliliter. How many steps do we have here? We have 1, 2, 3. So our tick marks down here are going to be 0.33, 0.67, and then 1. And remember that this is like percentage of cosolvent, or I guess ratio of cosolvent. So over here, this is on this side, I'll draw in a different color, 100% ethanol. And then over on this side is 100% water, right? And this solubility curve is going to go up as we draw. So if we draw this, this is our solubility. I'm going to draw in another color. Sorry, so many colors here. We're at that 0.1 milligrams at 0. But if we're at 1 milligram, we're at a cosolvent of 0.33. So that means that here there's kind of, for each 0.33 ethanols, there's going to be 0.66 waters. And that'll get you a solubility of 1 milligram per liter. Over here, if we go up again, we reach this 10. So now we have 0.66 or 0.67 of ethanol, and now there's 0.33 water. And then at 100% ethanol, we get 100 milligrams per milliliter, kind of like the problem said. So essentially, this is just asking for the point at which it's 10 milligrams per milliliter. You can see here that that's actually 0.67, which is what we have right here. Again, graphically, that's kind of hard to really conceptualize, but the way I just like to think of it is that since we're counting by tens on the one side, we're essentially counting by ratios on the x-axis and counting by the concentrations on the y. Just kind of do the step I did where I bounced between these numbers and just draw it out, right? If you go 1, 2, 3 this way, you go 1, 2, 3 this way. If we were trying to get to like 1,000 milligrams instead, it would be a little different. The marks on our x-axis would be, because remember, from 0.1 to 1,000, we'd have to do another bounce. It would be 4 bounces. So you'd start at 0, you'd go to 0.25, you'd go to 0.5, you'd go to 0.75, and you go to 1. So you're kind of doing 1 divided by your number of bounces, which 1 divided by 3 is 0.33. We're counting up by 0.33s in this example. But if we were in our 1,000 example, 1 divided by 4 is 0.25, going up by or 0.25, I'm sorry. We're going up by 0.25. So I hope that makes sense. I hope this video has been helpful. Feel free to rewatch it if you need to. These problems are also posted by Dr. Casting, which is super nice. But I hope just me showing how to work through these problems and think about these was helpful. But with that, thanks so much for watching, and I will see you in the next one.